Hello everyone. So in the part 1 of this video, we have talked about the Laplace equation and we apply this to the case where you have a temperature distribution on the metal plate, where on one end you have the heat source where you have T equals to 100 degrees, and on the other end we have T equals to 0. But in this case, we assume that um, the plate is going to extend infinitely to in the y direction, right? So we have done that and we solved and we got the equation which we have plotted. So in this video, we are going to look into a more realistic case where the y is not going to be infinite, but rather we have a finite value for the y, and we will see what is the difference in the equation. So again, this is the metal plate that we have considered earlier, uh, but now the y now is equals to 30. So in the first video, we said that y is going to be infinity, so it's going to be a very long metal plate. But here we have a y equals to 30, and then as usual, we are going to be interested in the temperature in the center of this metal bar where there is no heat source and the Laplace equation is valid. So now as we have done, we want to find the temperature, the function representing the temperature distribution as a function of x and y. Right, so now I have written back the temperature, the general solution for T. Here is the x component and here is the y. And in this case, when we have a realistic case, right, so we have a finite value for y, so, and this y equals to 30, which we assume to be the length of the metal bar, you have a t equals to 0. So when you have a finite case, then you cannot kind of like ignore, you kind of you don't care about this exponential ky, because if you remember what we have done, we say for the infinite case, semi-infinite case, where your y is going to extend to infinity, right? So when your y is going to extend to infinity, and exponential ky is not going to be a solution to your differential equation, partial differential equation. So you say this is not going to be the solution, and neither was cos kx, because this doesn't fulfill another boundary condition. So in the previous example, part 1, we say the solution is sine kx multiplied by exponential minus ky. But here you cannot just remove this exponential ky, so you have to take this into account as well. So the best way is to combine them, take a combination of the two of them, but try to figure out some ways in which they fulfills the boundary condition. So the boundary condition is given by here. So at the end tip of the metal plate, that is y equals 30, your temperature is going to be 0. Okay, so one way to do that is to write it in this form, right? So here I leave out A and B, and we will see how to kind of like guess what is A and B, right? So here I've written instead of exponential ky, I've actually written exponential 30 minus y, and here you have exponential minus in bracket 30 minus y. Right, so the idea was, now if let's say I put y equals to 30, so y equals to 30, then this I'm going to get exponential 0, so this is going to be 1, and this is the same as for this term. So therefore at the end I have a minus b equals to 0 and a equals to b. So from this form we know we know that this fulfills the boundary condition, as we have seen, provided that a is equals to b. So now the whole idea was then to choose a suitable value for a and b. So you can choose 1, you can choose 2, etc., right? But if you remember from your trigonometry, you will see that if you put a equals to 1/2 and b equals to 1/2, and this is going to be a sine function, a hyperbolic sine function. So this is sine 30 minus y. So now you have a very kind of a very clean expression for this expression if you choose a equals to b equals to 1/2. So as we have done in the first part, right, you will see that the sine kx multiplied by sine 30 minus y, uh, will not be able to fulfill one of the boundary condition, that is at y equals to 0 you must have t equals to 100, right? So what we have done in that earlier video was to kind of taking a superposition of these values, these functions with different n. So this is going to be the same in this case. So you have a sine n pi over 10x, so this is your k, and sine 30 minus y, but then here you have a increasing n, right? So now you need to determine what is the coefficient Bn, the Fourier coefficient, and here I leave it to you as an exercise. Just for a while. That is, you must find what is Bn, provided that when your y is equals to 0, your t is going to be 100, right? So you can pause the video now and you try to solve this on your own, and you should get the value for Bn to be 400 divided by 6195.8. So this is your sine 30 divided by n pi. Right, so this is a solution that you should get. So what I will do next will be to actually show you the derivation steps as a reference. Alright, so I hope you have tried to work out the solution by your own. And here, what I show on the screen now is the solution for the how to get the Fourier coefficient Bn, right? So now, as I have done before, I multiply both sides by a sine function, sine x n pi over 10x. So in fact, this should be m rather. So the point is now this is summation. So when n is equals to m, so you will see that this two is going to be sine squared, right? So here when n equals to m, I have Bn. The summation sign is no longer there because I'm looking at n equals to m only. And then I have sine 30, and this is going to be sine squared n pi over 10x. So we are going to integrate over x from 0 to 10. So here I just remove this, and this is the usual technique for integration, a sine squared function. So I change this to 1 minus cos 2 n pi over 10x divided by 2 for the whole expression here. And then here I will put x equals to 0 to 10. So at the end of the day here I will get on the right hand side Bn sine 30 divided by 2 times 10. So on the left hand side here, this is 100. I take it out and I just integrate as usual and put in x equals to 10 to 0 to 10, and then finally I will have this expression over here. So here you see there is a 1 minus cos n pi, and now depending on the n, your left hand side is going to change, right? So here you see if my n is an even number, so let's say for example n equals to 0, so this cos 0 is going to give you 1, so 1 minus 1 is going to be 0, so it means my Bn is going to be equals to 0 if n is even. On the other hand, if n is equals to an odd number, so this is going to be a negative 1, but then you multiply by this negative, so it's going to be positive 1. 1 plus 1 is going to be 2, so you will get 2000 divided by n pi. So now you have this on the left hand side, you have this, and on the right hand side you have this one, this expression here. So you kind of rearrange so that you have Bn equals to 400 divided by sine 30 divided times 1 over n pi. So this is the coefficients that you want for the function representing the temperature in the metal plate. So to close this discussion, we are just going to look at the plot and see how does it differ as compared to the first part of this video, right? When you use the semi-infinite approximation. So here to get to plot, I'm going to use the same parameter. I'm going to use x equals to this linear space from 0 to 10 and y from 0 to 30, and I make a mesh points, and then I will set for this n equals to 3, and the initial value t is equals to 0, And what do I do next? It will be to make a do loop now. Then this is so this is the new equation. I have t. This t is for the purpose of the do loop. And then this is the coefficients, the new one that we have obtained, the 400 divided by I pi sine 3 I pi. So the I is actually n, right? So but then now this is a part of the loop. um and then I have the sine function again and multiply by the sine function. So one is sine, one is sine, and now in loop, and I can now plot this function, right? So here you see this plot is exactly the same like what you have seen in the first video, right? So it looks exactly the same, but then now what about the temperature at the specific point? So to compare, we will just use the same point that we have considered just now. We say x equals to 5 and y equals to 5. And if you remember, what we got in the previous calculation was about 26.1 degrees Celsius. So at this point, the temperature is 26.1. But what about this new equation, right? So again, we set t equals to 0, and now we use the same loop. And then we see this is the result. So the result is exactly the same. You have 26.468 for n equals to 1, n equals to 2, there is no change because my coefficient is equals to 0, and n equals to 3, I have 26.087. So this is in fact the same value that you get when we do the calculation with the semi-infinite approximation. So here this shows that the approximation that we used in the first video is good, right? So because we are talking about the region where there is no source, so this assumption that the metal plate is going to be infinite in the y direction is actually good for this calculation, right? They gives you the same results. But nevertheless, here what we have done is we have obtained a equation which is more realistic, right? So this is in terms of a sine function, a hyperbolic sine function, as compared to the exponential minus ky which was obtained earlier. Alright, so that's all for this example. So I hope you have enjoyed the video, and try to work on the calculations, the derivations, how to obtain the Fourier coefficients and so on, to make sure that you are very familiar with this with the mathematics behind this example.